Thank you. I wasn't expecting that introduction. It is true that I used to work at Trifork. It's many, many years ago, and I actually still remember my job interview. Although I must admit I was remembering it as Jan, the CEO of Trifork, that was part of it, but I'm sure you were there as well. But what I remember, I came straight out of university, and this was my first job, and I interviewed for a software engineering position, developer position. And I remember saying as part of the job interview that, I actually would like to have more responsibility. I might want to go into management at some point. And they were just staring at me like, nah, I don't think so. I think you're wrong. I don't know why. Somehow I managed to get hired anyway. But what actually ended up is I'm now a manager. So it turned out that, though I didn't know it at the time, that was actually what I wanted to do, and then what I ended up doing. So thank you for the introduction, and thank you so much for this opportunity to come and talk about some of the cool things that we're doing at GitHub to help with application security. My name is Karl Krukow, and as you just heard from the intro, I have an engineering leadership position at GitHub for a team that is building some of the cool technology that we'll be speaking about today. Now, you probably know GitHub as this remote-first global distributed company. That's sort of one of the things it's well known for. But you might not know that we actually have quite a few people working here in Denmark, including here in Copenhagen and in Aarhus, who are working on some of the technologies that I'll be showing you today. So I actually think that's pretty cool that we're contributing to GitHub, contributing to the home of open source, as we like to call it, and also trying to make that more secure. And this is obviously also a plug in case you're changing jobs at some point in the future. You may want to consider coming and working with us. So what I want to do today is give you a sense of 3 security challenges that we face today as developers, and how we think at GitHub that we should address those challenges. And in order to make it a little bit more interesting, I think I'd like to look at those challenges through the lens of 3 real security incidents that happened over the last 5 years or so. So I hope you're up for that, and with that we're gonna dig straight in. So does anyone know Fortnite? Big game, yeah, does anyone have kids that's playing Fortnite? Yep, pretty popular game. So this incident was quite interesting. In 2018, there was a team of security researchers from Israel that essentially found a vulnerability on the Epic Games platform, which is the company behind Fortnite, that would allow an attacker to essentially take over the account of any player that was subject to the attack. So if that were your kids, that would be things like logging in, viewing their private information, or even eavesdropping on the chat conversations they have with other players, maybe even impersonating them. Exactly the kind of stuff you do not want happening to your kids. Also, at the time, it was pretty big, like it's even larger now, but at the time it had 125 million users, and it accounted for about half of Epic Games' revenue, and they were evaluated at something between $5 and $8 billion. So you don't really want an incident on this thing. So how did the attack work? It's a little bit complicated, but we can look at sort of a few of the basic components that are part of the attack. So it starts here. So what the researchers discovered was there was an old site called UT 2004 Stats. Does anyone know what that might be? Yeah? Unreal Tournament 2004. Is that an active game? No, not really. But this site was still running. It was up there. It was running in production. It wasn't really being actively developed on, but it was still out there. And what this research team found was that this site was subject to a so-called cross-site scripting attack. And if you don't know what that is, it doesn't really matter too much. The point is that you can think of that as the attacker is able to put in their own JavaScript code into the site, so that when a user visits the site in their browser with their own session, that potentially malicious code will be executed. And so how did it work? It was actually fairly simple. So this lovely site had a URL parameter you can see up here, where it says search name equals something something, and then you see alert, and then some weird characters. And if a user would click this link, they would go to the site, and then you can see sort of the proof of concept of the exploit here. There's a little alert box that says XSS that proves that actually the code that was passed as a URL parameter gets executed. So interesting, but not particularly useful on its own, right? This was not really an actively used site. It couldn't really be used for anything. However, next, the researchers turned their attention to the general login mechanism for Epic Games. And here, they were essentially able to craft a link so that if the user clicked that link, they were basically done. They would be able to take over that account. So it wouldn't take more than clicking a link. And of course, I know you were going to say, yeah, we all know we're not going to click links from strangers that look weird, right? But in this case, the link actually kind of looked pretty decent. So you see up here, it's using HTTPS. It's obviously secure, right? That's like the definition of what you should click on. Turns out no. And also, it looks like it's going kind of to the right place. Now what happened here was that the system was using OAuth, so this experience that you know that's called like sign in with something. So you can see a button like that on your right that's saying like sign in with Facebook, for example. And then you go to Facebook or Google or whatever, you go through the sign in experience, or maybe you're already signed in, because who isn't always signed into Facebook or Google? And then you get redirected back, and with a token that is then used to authenticate against Epic Games. Now you might be able to guess what happened, but you see this redirect URL thing. Now the attackers were able to essentially manipulate that to put in their own content there. And as you can probably guess, what they were able to do was link into this old site that was vulnerable to the cross-site scripting attack, the UT stats game. And then if you see the little weird code where it says script, %20 source, blah, 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 they put in a payload that was a script tag that was pointing to a script that they controlled, essentially. So in other words, the user would go through the flow, but rather than going to the accounts page for Epic Games, they would be redirected to the other site, but they would still have the context, the token that would allow authentication. The malicious script would then take that, send it off to a malicious server, and then you essentially were able to take over the account. So, not good. And that sort of takes us to our first security challenge that I want to talk about, which is, all right, and so I forgot to say, what they should have done, of course, was to restrict the sites that were allowed to be redirected. And they essentially had this pattern to be the sites allowed to be redirected. So, what I was going to say next was, the first challenge is your code, all the code that you're writing every day in your jobs. We do something called the State of the Octoverse, which is a report that we do at GitHub where we sort of review different aspects of all the code that we see on github.com. And probably not unsurprisingly, what we found was that there was more and more code. And the more and more code we have, the more and more vulnerabilities we have. Probably not surprising. It's not very great though, because we all tend to write more code, not delete code. And also, if you look at the slope of the bottom of the graph, the security threats piece of the graph, it doesn't really seem to be improving. Like it's not going down, right? It's maybe even increasing. So we're not really getting better at writing secure code, it looks like. And that's understandable. If you think about what developers need to do today, they need to learn a lot of things, right? They need to learn programming languages, different frameworks, libraries, cloud technologies, testing, architecture. Are we also going to ask them to be security experts? That's maybe a big ask. Then, of course, what some companies do is that they have application security teams. So those are centralized teams that will help other teams build secure applications. But those teams tend to be small and centralized, and they're serving a lot of different development teams. So what would actually be better was what if we had a security-minded engineer or a security researcher that's embedded within every development team, looking at every line of code, reviewing that for security vulnerabilities. But unfortunately, that's not really where we are. And of course, our applications, they don't just contain our code, they also contain a lot of other stuff. And that brings us to our next story, which was the story of Event Stream. Now, Event Stream is a very popular open source JavaScript library. At the time, it had, over 1.5 million weekly downloads, and now it actually has over 3 million weekly downloads. And this compromise was quite interesting. So in this case, it was an open source package. And we all know, like, the spirit of open source is we all collaborate to make the world better. So we'll take contributions from different people and share them with the world so everyone can benefit from them. And that's exactly what happened. So in September 2018, there was a user called Write9CTRL, which started making contributions to this library. So valid, good contributions, improving the library. And over the course of 2 months, they kept making good contributions to this library, eventually gaining the trust of the library maintainer. And then at some point, the library maintainer decides, you know, I don't have time for this stuff. I need to like hand this project over to someone else. And that became Write9 control. What happened then was that it turned out that Write9 control was a malicious user, and over the course of the next month, they introduced into this package a dependency on a third package, or a second package, I guess, that was called FlatMapStream. And on the surface, this other dependency, FlatMapStream, seemed quite sensible. It was like a utility library, kind of makes sense to start using that, factor that out as a separate thing. And if you were to go and look at the source code of this new dependency, FlatMapStream, on GitHub itself, it looked fine. It was like, cool, utility library, does some functions, that's great, let's use that. However, what happened was that if you were to run this at runtime, a slightly different version of this dependency was running. And that was containing a highly obfuscated and highly targeted attack. So it was obfuscated in the sense that there was some code that was encrypted with a certain key, and that would only become active if if the code was running in the context of an application called Copay, which was a Bitcoin wallet. And if it were running in that specific context, it would sort of wake up, become active, override one of the functions. That's actually what you're seeing in this code dump on the blog post. And it would override a function called getKeys, steal whatever data was propagated to that getKeys, put it and send it to a server, and then otherwise return the original result, so pretend as if nothing happened. So enabling effectively the stealing of Bitcoin for the users of this particular application. So very sophisticated, like taking several months, gaining the trust of an open source maintainer, making valid contributions, eventually taking over, introducing a highly obfuscated, very targeted attack that was running all sorts of places in the world, but only became active in a very small context. And so that's describing the next challenge, which is the code dependencies. As we talked about, we're increasingly depending on libraries, frameworks, open source in particular. And we're seeing an increase here. And in the State of the Octoverse report that I talked about before, a couple of years ago, we saw that more than 90% of repos on GitHub.com use open source dependencies. Again, probably not surprising, and probably a good thing, because the same report also found that developers who are able to adopt open source without friction, without a lot of approval or review or other barriers to adoption, are significantly more productive. They're able to move faster, get things done, because they're able to reuse code, essentially. But it also brings this trade-off, like, do you want fine control of the dependencies, or do you want speed? You kind of want both. So what are we going to do about it? And of course, you might think, well, it doesn't really apply to me. You know, we have a very small, carefully curated set of dependencies for our software. However, the thing with dependencies is you kind of buy one and get 68 for free. And so what do I mean by that? What I mean is dependencies tend to also have dependencies. and those dependencies tend to also have dependencies. And if you start adding those up, and again, here is some data where we look at the median number of dependencies per repo, per language ecosystem at GitHub. And let's just take JavaScript. If you have a median of 10 dependencies, you would have a median of 683 indirect dependencies if that were being pulled in sort of for free without necessarily you asking for it. And so if you think about it, it means that 98% of your dependencies are actually indirect transitive. So do you really have control over that or not? And of course, I realize that in different ecosystems, it's not quite as bad, but still in those other languages, it's still the dominant factor is still the indirect dependencies. Anyway, the event stream thing, at the time of that event, so to speak, there were 1,600 other packages that depended on event stream. And so if you were depending on event stream, which you probably were if you were using JavaScript, you would be carrying the attack, even if you weren't subject to it. Unless, of course, you were building some Bitcoin system. I don't know, is anyone building any Bitcoin systems in here? No, we're done with that stuff, okay. Anyway, it's fixed now, so you didn't need to worry, even if you are. And so this brings me to the third story that I wanted to share with you, and it's a little bit embarrassing because it actually involves GitHub itself. So this was an event in April 2022, where our security team discovered that there was an attacker that had been using stolen OAuth tokens, those OAuth tokens again, to get access to GitHub data, essentially. So those were tokens that were extended to third-party providers, so Heroku, which you might know, and Travis CI. So for example, let's just talk about Travis CI. That's a cloud-based CI/CD system. And because it needs to build and test and possibly deploy your code, it needs access to the code. And so it needs this token to talk to GitHub and download the code, essentially. And those were leaked. And of course, the GitHub security team discovered this, and they worked with the customers, notified them, remediated the problem, mitigated the problem, worked with the partners, revoked the tokens, all the things. But they also did an investigation of what did the attacker do? Like, what was the behavior of the attacker that had this access? And what they found was the attacker used the token to call the GitHub API to enumerate what are all the GitHub organizations that this token has access to. And then for each of those organizations, enumerate all the private repos, and then selectively start cloning some of those repos. So why would an attacker go through this risky business of actually launching an attack in order to clone some private repos? What do you think? What? Ah, yeah, my precious. Yes, precious secrets. That's exactly right. So what we believe that they were doing was that they were scanning the code, downloading the code, and then scanning it, hoping it to find secrets, tokens, API tokens, credentials, passwords, anything that would enable them to pivot their attack and get access, say, to backend cloud infrastructure, something like that. And so this is an example of the third, and actually quite a large risk, third class of security problems, which is the secret for dependencies. So more and more code, more and more dependencies, but we're also increasingly using services, cloud services, SaaS providers for doing all sorts of things. And again, it enables productivity. It's great. We don't have to create our backend storage. We don't have to write functionality for sending emails or text messages or whatever it is we need to do. But it also means that the code needs access to these tokens. And what's the absolute easiest way to give an application access to a token, an API credential? Easiest way. Anyone? Where? Allow all. But how does the application, when it's running, actually access the secret? Hard code the secret into the source code. Password equals, here's my password, or API token equals whatever, right? And that happens a lot. So here's some data that shows number of, in this case it's GitHub access tokens, leaked in public repositories. And again, we see an increase here, fairly large increase over time. And sort of what this amounts to is about 250 access tokens being leaked by developers on a day-to-day basis on github.com. Okay, so we have the three in summary: the code, you're writing more and more of it every day. Your dependencies, do you understand what they are? Do you understand if they are safe? And the secrets, can you keep them? So what are we going to do about it? How should we approach this? Well, we already know, right? We're going to shift left. We've all heard about this before. Shift security left. I'm sure you've heard about this before. It's pretty intuitive. It basically means that the earlier in the development process that you can identify and fix vulnerabilities, the cheaper it is. So obviously, if there's a data breach, that can be incredibly expensive, depending on your business and the scope. But even if you're fixing something, 6 months after development, it's in production, you may not remember the code, you have to find it, that's significantly more expensive according to this report. And if you're able to pull it all the way to development and fix it while it's active in your head, it's super cheap. It's maybe an hour or something for a developer. The thing is, this report, where this stuff is from 2012. And how are we doing on this? Have we nailed it? So I'm curious now, can you do a show of hands? Who's working as a developer or working in a development team? Raise your hand. Is everyone? Yeah, developer conference, awesome. Okay, now be honest. Raise your hand if you feel like, yes, we've nailed it. We've got this shifting security left. That's our thing. Two people. I want to give you a hand. It's always one or two. I'm curious how you've done it. Maybe we can do a Q&A in the end to figure this out. But it matches my experience. We haven't really solved this because it makes sense, but how do we do it in practice? So that's really what we want to address at GitHub. And we think, in some sense, we have some unique strengths being GitHub that will help us make this a little bit more realistic. So what are those strengths? The first is we've been building tools for developers forever. GitHub is, 15 years old now, something like that. And at the heart, it was always about making tools for developers, making things more accessible, making Git accessible, creating the pull request experience that hopefully many of you are using today. So it's sort of in our DNA. So for us, the developer is the customer, not the application security team or something else. We want to create compelling experiences that actually fit the developer's workflow, whether that's in an IDE or it's in the pull request experience, and then empower developers to actually understand what are the security risks and how do I fix them, as opposed to having to go to some separate system that's managing vulnerabilities or something like that. The second strength is open source. So obviously we have a lot of the open source code hosted on GitHub itself. And that gives us, in some sense, an opportunity, but also an obligation to try to help secure that open source software. But in many cases, we also control more than the software, or we have access to more than the software. We also have the infrastructure that builds and tests the software, publishes it. If you are familiar with something called GitHub Actions, that's used by a lot of people by now. It's quite popular CI/CD system that GitHub runs that's used to build and package the open source software. And in some cases, we also have the distribution channel. So we have GitHub packages where you can download packages from a package registry. And we acquired NPM not too long ago. So we also control that major distributor. And so with all that, there's a lot of responsibility and power and all that stuff. And we really want to try to improve that entire supply chain to make open source secure. The final thing is more of a, let's call it a mindset thing, which is our way of thinking is really about community, collaboration, and open source. And the question is, can we make security, software security, more collaborative? Can we make that more like an open source thing where we are all collaborating, helping each other to secure each other's code? And I know that sounds a little abstract. I'll make it more concrete in a minute, but that's an important mindset. And in fact, we're doing some of that now. I'll give you a simple example of this with the something called advisory database. So this is a large, free and open source database of security advisory, CVEs, that is maintained by GitHub itself and is curated by a full-time team of curators that are looking through new advisories or potential advisories that are coming in, checking whether they're valid, working with open source maintainers to remediate them, and then publish the CVEs eventually. And so this is sort of a good example of how can we have security teams collaborate with developers in the open. I mean, obviously, once during the advisory, it's being handled closely, but once there's remediation, it is published in the open, so everyone can update their dependencies. And I think it's a really good example of this open source mentality for security. But we're doing more, and that's where this advanced security stuff comes into the picture. So you can think of advanced security as a collection of tools or a collection of products that are all built with this mindset I was talking about, empower developers to understand, remediate, and prevent security vulnerabilities. And I'll talk about each of those. In theory, you could sort of have a talk on each of these components on its own, so I'll just give a very brief overview of them, but happy to chat to you if you want to talk about some of these in more depth afterwards. But one of the key points I want to make here is that due to this application and this mission to secure the world's software that we have, it's literally our mission in our team, we're making this free for all public repos, all open source projects. So if you are a open source project maintainer, if you have public repos, definitely encourage you to go turn this on, let it help you secure your projects, and also give us feedback on how the thing's working for you. So let's look at each of these components. So first is secret scanning. So as you can probably guess, secret scanning is about scanning your code and finding API tokens, essentially, other secrets, all the credentials that you might have in your code. So the way this works is that it obviously scans your code and detects certain patterns. So we collaborate with 75 different providers of API tokens and detect their patterns. And for some of them, we're even able to check in real time if that token is still active and valid. So you can sort of prioritize the secrets that are found that are actually still in production, still valid. However, one important point here, well, two important points. One is that this obviously scans the entire Git history. It's not just like the current version, because if you had a secret and you maybe decided to delete that and commit and push, well, that secret is actually still there in your Git history. So we're going to scan for that. The second point, and that's what you're seeing in the screenshot, is that we also want to go from detection to prevention. And so there's this thing called push protection. And the way that operates is that if a developer is typing some code, they type in a secret. In this example here, we have a Slack API token. And they try to push it. Then push protection will say, oh, wait a minute, we've detected this. Are you sure you want to do this? And then you can see there's a link that goes to GitHub where you get a dialog where you get more information about the secret, what we think it is. And then as a developer, it's sort of your choice. Do you want to override and say, no, I know what I'm doing, let me push? Or do you want to reconsider, so to speak? Or do you want to potentially remediate or revoke the secret? So this is an example of integrating into the developer workflow, hooking in, and then preventing secrets from coming up. All right, so that's secret scanning. Next up is supply chain. So this includes dependency graph. Is this readable? Yeah, this is readable. This includes something called dependency graph, which is the thing you're seeing here, which does two things. A, it shows you what dependencies you actually have, including transitive dependencies. But maybe more importantly, it connects with the advisory database and says, for any of those dependencies, whether direct or indirect, are there any known security vulnerabilities? So it gives you sort of an overview of your supply chain. And then you can go do something about that. So that's, again, an example of detection and insight that's given to developers. But once again, we want to go from detection to remediation. So there's something called dependency review. And this is something you can integrate in your CI/CD system. So in this case, it's a GitHub action that's running. I'm here I'm creating a change to my project. I'm introducing a dependency on log4j 2.13.1, which has a known vulnerability. I'm not aware of that as a developer, but dependency review scans my dependencies, collects all the indirect dependencies, checks that against the advisor database, and then posts a comment here and says, wait a second, you have a vulnerable package that you're about to introduce. So trying to go to prevention again. You can then set up policies, is it possible to merge if there is this failed check or not? That's up to your organization, but you have the option here. An interesting thing about this is you can also use this to manage open source licenses. So say I only want to include dependencies with these licenses, or I do not want to include dependencies that have these specific licenses, which is also a common problem. Okay, but the way that we usually work is we don't introduce old dependencies with vulnerabilities into the code. What we rather do is at the point we're adding a dependency, we're using the latest version. It doesn't really have any known vulnerabilities, but then over time, a vulnerability is discovered in that particular version that we're using. That's usually the way things go. And that's where dependabot comes into the system. So if dependabot security updates is running, what will happen is if a vulnerability becomes known in a dependency that is being used in this particular project, it will automatically create a pull request to suggest a update from this case 4.17.15 to 4.17.19 that is no longer vulnerable. And in the best case scenario, all you need to do is hit merge and you're done. You're no longer vulnerable. Of course, we all know that in practice it could be maybe a little bit more difficult because maybe this version of the package behaves slightly differently or has a breaking change. So in that case, you obviously need to do something. But I was actually looking at if you're familiar with the ThoughtWorks, what's it called, technology radar, came out a few days ago. And they actually were looking at dependabot and saying, we are at the point where we are at least assessing, if not recommending, to almost auto-merge this in the condition where you have an extensive automated testing suite. So unit test, acceptance test, performance test, end-to-end test. Basically just merge this. And that allows you to have a very, very fast time to remediate. As soon as the security vulnerability is there, PR is created, gets automatically merged, and you have almost instant remediation, which is quite powerful. All right, so that was supply chain security. Now I want to talk about my favorite part, because it's the stuff that the team that I'm part of is working on at GitHub, which is code scanning. And this goes back to the first security challenge we were talking about, the cross-site scripting example, which is essentially the code that we all write today, and finding vulnerable patterns in that. And remember when I was saying that it would be much greater than having all these centralized application security teams. It would be much better if we had a security engineer in every development team. And that's sort of the vision of the experience that we want to try to build with code scanning. So rather than having an actual security researcher or engineer, what you have instead is a bot. Bot scans the code and participates in code review if it spots any vulnerabilities in a particular change that the developer is suggesting, just like a colleague would do when they were doing code review. So let's look at an example for that. So here's a change. Someone's introducing some sort of token in emails and then check them for validity when they click verify your email link. That's a pull request. It has a bunch of changes in lines of code. There's a GitHub action that's running, and you see that as the GitHub code scanning bot here. Found potential problems. It says that on this line, there is a potential SQL injection problem because you have a database query that's built from essentially sources you don't control. And so you can see there's then a reply button, and that means that this is just a normal code review. The development team can then have a conversation. Is this a problem for us? How are we going to remediate it? How are we going to address it? And that's what I mean by fitting into the developer's natural workflow. Of course, behind the scenes, there is some sort of engine that's actually doing this work, the difficult work of understanding the code and figuring out if there are vulnerabilities in it. And for that, we have multiple options. So we have a number of different partners. In fact, I was just talking with Francesco from Erlang Solutions, and they're also building their own engine for Erlang and Elixir. And so if they wanted to integrate and have their stuff working on GitHub, they could potentially do that. So we might do that. So that's the partners, but we of course also have our own engine, and that's what I want to touch upon briefly next. And that engine is called CodeQL, and that's GitHub's own powerful code analysis engine. And it's the default engine that you would use if you were using code scanning out of the box with GitHub. So CodeQL has a long history. It was let's say a research project that came out of University of Oxford over 10 years ago, done by some very clever programming language PhD students and professors. And then from that technology, that research technology, they founded a company called Semel. And then in 2019, GitHub acquired Semel and started integrating this technology, this CodeQL technology, into the GitHub platform itself, as well as continuing to improve the technology and make it better and more powerful and faster. So let's talk a little bit about this. And this, again, it's a whole day type workshop on its own, just to get started, to really understand. It's like learning a new language, because it is a new language. But we can get a sense of what it is today, and you can get a sense of whether you want to invest more time in learning about it from what I'm going to say next. So the thing with CodeQL is that it is a static analysis engine that is semantic in the sense that it will actually parse your program, build the abstract syntax tree, and do a bunch of analysis on top of that, including something called data flow analysis and taint tracking analysis. And if you don't know what that is, that doesn't really matter too much, but you can think of the taint tracking stuff as that is the power in the analysis capabilities that you need if you're going to find things like these cross-site scripting attacks, where essentially the question you want to answer is something like, is there a flow of data in the system where an input parameter which is untrusted enters the system, that could be a URL parameter, is then passed through your program using a different function calls, assignments, all sorts of flow in your program. Maybe it's called to functions and libraries, maybe it becomes sanitized, maybe it doesn't. Eventually it ends up in a dangerous place. And so dangerous place depends on the security threat we're modeling, but that could be a call to the database, it could be manipulating the DOM in the case of the client-side cross-site scripting attack. So being able to answer a question like, is there a flow that goes from untrusted, passes through the program, does not go through a sanitizer, and eventually ends up in a dangerous place? That's a really difficult question to answer, and you need sophisticated analysis to do that precisely, and that's what it does. And so it's maybe a little bit unique in that the approach is that it considers code as data, and it literally builds a database of your code at every commit, at every version point. And then when you want to ask questions, does this pattern exist at this point in the history, you run queries on that database. And the query language that you use to do that is called QL. And this is this slightly weird but powerful object-oriented logic programming language that's used as a query language for this database. And it's highly specialized to run these analyses in a performant way. So it's kind of a nice abstraction. Build a database, run a bunch of analyses as queries to that database. However, I do want to say that you don't need to learn all this stuff to use this technology. It comes with what I call batteries included, which means that we have our team ourselves, as well as the security lab team at GitHub. We are building a large collection of queries that just work out of the box, so to speak. So if you just want to run it as a black box with the built-in queries that find a large number of security problems, common security problems, you can just sort of run that and it works. And we're constantly making that more performant, as well as adding more and more queries every year. Another point that's, again, more of a philosophy is that we are targeting a low false positive rate. Again, the point is we want to create good experiences for developers. And if you create a tool that creates a lot of noise, that says there are all sorts of problems in this code, and then when you look at it, it's not really real, you piss off the developer, and they're not happy, and they ignore the findings. So you don't want to do that. So we try really carefully to keep the false positive rate very low. So if the tool says there is a problem, it's highly likely that there is actually something there, or maybe there's not, but then there's sort of, you wouldn't be disappointed at why the tool might thought there was a problem. And that's a judgment call, and it's a data problem. It's never perfect, but that's what we're striving to do. And then the final point is that since there's this query language, you can obviously write your own queries, right? So it's extensible. If you want to go and learn this language, you want to have specific patterns that you want to search for in your code base, you can do that by writing your own queries. That also has an interesting application, which is, you remember a couple of years ago, or maybe is it only 2 years ago? I don't forget, or I don't remember. But there was this Log4j shell attack. Do you remember that? It was a big thing. Yeah. So one problem you may want to solve in that situation, like right when that happens, one problem you want to know is, am I affected? Or more generally, like which repos in my organization, which maybe has thousands of repos, are actually affected. So what our team did in that case was we wrote a query that would say, detect the type of code pattern that would be vulnerable to this specific injection attack. And then there's a system that is able to run that across all repos of an organization. So you can say, prioritize this repo, and this repo first, because that's highly likely to be vulnerable to the actual exploit. So that's a pretty powerful thing. We call that multi-repo variant analysis, that system that does that. Anyway, I also wanted to show you a simple example of, just to give you a sense of what this query language looks like. So let's do that. It's kind of fun. So do you know JavaScript? Have you read the book JavaScript, The Good Parts? It's a really tiny book. A tiny book, no. It's worth a read. In that book, the author talks about the good parts of JavaScript, but he also says there are a few things you should avoid in JavaScript. One of them is calling the eval function, which, if you know that, it's a function that takes a string and then compiles it as code and then runs it immediately. So obviously, if an attacker can control that string, they can essentially run code inside your application. Limited use cases for that function, although when you need it, you need it. But there are actually a bunch of other functions that are the evil twins of eval. One is called setTimeout, the other is called setInterval. Maybe you know that from your JavaScript programming. And you know that those functions exist in variants. In one variant, you can call it with a string as the first parameter, in which case it compiles that string just like eval, runs it just later. Or you can call it in a variant where you give it a reference to a function, and then it's that function. So the second variant is fine, because that's a reference to a function you wrote. The first version is not so fine, because, again, if the attacker might control that string, you have a potential injection attack. Doesn't really matter too much. The point is, let's write a query that tries to find all instances of the following. Like, if there's any call to set timeout or set interval, but not just any call, it should be a call where the first argument is a string rather than a function. Not super advanced, but also not trivial if you were to like do a code search or write a little regex thing that would search for it. So let's look at what that looks like. Oh, I forgot to add, there's one more thing this checks for, which is use of document.writeLine. Does anyone know document.writeLine? Does that tell you how old I am? You don't know it? No, okay. Don't use it. It's a way to directly write to the DOM. It's something we did in the old days when you were doing web programming, I guess. So if you call document.writeLine, you will write directly, let's say, the HTML source code that you want the browser to show as a string. And then again, if you do that and the attacker control that string, they could write a script tag that points to a script that goes and executes something. So those three patterns, we want to find those with one query. So let's look at it. So as you can see, this looks a little bit like SQL. You got like some select where from stuff. But you also have like instance of, so maybe it looks a bit like Java, but it's nothing like Java. But as I said, it's an object-oriented query language, logic-based query language. So it has classes, but they mean something slightly different. Anyway, we can sort of still read this. So this is saying, let's take all the data flow nodes in the program. And what are those? You can think of those as interesting program points where data can potentially flow to. think of them just as program points in the program. But then filter, so you only get the ones that are instances of something we call document write, or those that are instances of something called set timeout or interval. And those are classes that we'll define in a second. So it's constraining to those two. And then what's the result? It's all the program points, select node, and then an error message. Avoid functions that use eval on strings as code. All right, so let's look at the classes. So here's document write. So this is a class that extends data flow call nodes. And so again, in QL, classes aren't something you use to create objects like you would in a regular object-oriented programming language. Here, classes mean a subset of values. So when I say document write extends data flow call node, it means that any instance of document write is a subset of data flow.call node, and those are function calls in your program, function or method calls. Okay, and so what is the subset? It's everything that satisfies this predicate where it says exist string write line, and then the instance should be a reference to a global variable called document, and then there should be a member call. So that would be the dot in JavaScript, so it's document dot or it's document square brackets. And that should be a member call to something which is a variable write line, and that write line string should match the regular expression write or write line. So this is a way to encode a subset of program points that have this particular shape. Make sense? Maybe like not all the syntax and that stuff, but like high level, it sort of identifies a subset of program points. Let's look at the other one, set timeout or interval. This is also function calls, so it extends call nodes. And it is the specific program points that satisfies this predicate. There exists a string fn, which is either set timeout or set interval. And this node is a global variable reference to that string fn. And then it's a call. But we also specify that the first argument, get argument 0, as an expression is a constant string. So that means we're not getting all the instances where you're using this function correctly. You're only getting the ones where you're passing in a constant string. Again, it's a fairly basic example, but gives you a flow of what these types of queries can look like and the sort of questions you can ask of your program once your program exists in a database. All right, so that's simple. Oh yeah, here's so the point I was making about customizing and extending it. So if I take this query and I put it in my CI/CD system to run along with all the other built-in batteries included queries, and I do this weird thing where I say I found this amazing document square brackets write line that I want to do, so I'm introducing that code, and then the bot comes and says, oh, avoid using functions that evaluate strings in code. Basically, it found that pattern with my custom query, and then that's integrated in the pull request. So our team actually does this, our development team. So they have a couple of patterns for Go code. They write the queries for that, and then they prevent those patterns from appearing. It doesn't have to be security, although the security is our focus. Okay, let's look at a slightly more sophisticated example. So I won't show you the code for this. It's a little bit more involved. But I'll show you the type of experience that this so-called data flow taint tracking analysis enables. So in this case, there's been a vulnerability found. We found a cross-site scripting attack, just like in the Epic game example. And the most important line is this sanitizer bypass security trust HTML, which is called with a variable called query param. That already smells pretty bad, but of course, we want more than just a smell. We want to actually know if there's anything dangerous that could potentially be in this variable. So because this query has been using the data flow analysis and something called a path query, it enables this experience where not only can we say there's something here, we can click this show paths button to essentially learn more about how might this happen in practice. You can think of this as like what a debugging type experience would be like. So what that says is that we start in step 1. There's this function, and it has this access, this route snapshot query params.q. I think it might be Angular JS or something. I'm not entirely sure. But this is the place where we actually access the URL parameter. And this can be potentially dangerous because it might be controlled by an attacker, right? Just like in the Fortnite example where you click a link someone sent to you. So this is the source. There are a bunch of steps that I cut out, steps 2 to 5. But then eventually you go down to step 6 where we say, oh, I noticed that you put this variable. So in step 1, you put the variable into query param, you do some stuff. In step 6, we notice that you change the query parameter variable by calling trim, which is fine, but it doesn't really change the nature of the risk. It's still tainted, right? Because trim just removes the white space on the side. It doesn't really filter for anything malicious. And then after that, oh, this is hard to see, but at the very bottom, step 7, that's where you're calling a method that we actually know is dangerous because it will insert the HTML directly into a DOM. And so you have like a debugging type or trace-like experience where you can see the entire flow because the analysis has this capability of data flow. And this is a very good example of what we mean by developer-friendly experiences. Make something that makes sense for the developer. Because what you really want to know is, like, that's fine, you think this is an issue, but is it really an issue? By the way, I forgot to say that we also, the show more thing gives you more information about what are cross-site scripting and what can you do to mitigate them. So there's also some documentation help there. Anyway, that's what I wanted to show you. One final thing I wanted to mention, which is I said that we're community powered. And what I mean more concretely, I can say that now, which is what we actually did before in the JavaScript example was we have some knowledge, information about code. I know that I read the book, and I read that if I call these functions in this particular manner, that's bad. I can actually take that knowledge that's in my head, write it as code, put it on GitHub, and contribute it back to CodeQL. And then every developer in the world who wants to use this can benefit from it. And that's what I mean by community-powered security knowledge. And that's actually what we do. So CodeQL queries are open source. And there are security researchers at Microsoft Security, at GitHub Security Lab, as well as third-party security researchers that do their research, i.e. find vulnerabilities, typically in open source software. Once they find it, they abstract it and write it as a CodeQL query to find all variants of that particular vulnerability. They possibly run it on different open source projects to see if there are others affected. And then they contribute that back to CodeQL itself. And then we have our own team of experts that then review that, validate that it's good, and then integrate it back into CodeQL. So every user that's using CodeQL will benefit from this. And that's, I think, actually really powerful because now it's a community open source driven thing and we can all help each other. In addition, we also have this bug bounty program to incentivize. So there's an example here, I'll share the slide and you can follow, where someone earned more than $2,000 by discovering a JNDI injection attack in Log4j. And that was validated and was like, yep, this is real, it has impact, there's a bug bounty associated with that. So this is something I really think is cool. By the way, if you want to try this out really easily, you can follow this link and use something called GitHub Codespaces. So just do like a cloud developer environment where you can play around with CodeQL. It's quite neat. All right, I am almost done, but I want to invite you to a conference. If you can go to San Francisco in November, it's November 8 and 9, I would highly encourage you to do that. But I know that's a long trip, so I want to invite you also to come join this event online for free. And as part of that event, you're going to hear about all the things that are coming in the space, including how we're using AI to make some of these experiences even more powerful for developers, including Copilot and including AI-powered features in advanced security. Unfortunately, I've been told not to tell you what's coming. That's supposed to be revealed in November, so I highly encourage you to go there. But you can think about what might you be able to use these large language models to do in this space, within this context. You can think about that question. All right. Thank you so much.
Sure.
Don't forget to rate the session, by the way. And thank
Thanks
you
a
so
lot.
much for listening. Happy to talk.
Yeah, thank you.